Hello and welcome to the Gulf Coastal Plains and Ozarks Landscape Conservation Cooperative's webinar presenting the results of a project entitled Changes in Southern Forested Landscapes Under Alternative Climate Change and Urban Growth Scenarios. Some background on the GCPO LCC. We are a part of a national network of 22 landscape conservation cooperatives that cover the entire U.S. LCCs focus on strategic conservation at a large or landscape scale that will be adaptive to future change. The GCPO focuses on a 180 million acre geography that covers all of Arkansas and Mississippi and portions of 10 other states centered around the lower Mississippi River. Today I have the honor of introducing our PIs. Dr. Hong He is a professor in the School of Natural Resources at the University of Missouri. His expertise is in landscape ecology and forest landscape modeling, and he has led the development of the Landis Pro Forest Landscape Model. Jacob Fraser is a research specialist and PhD student in the School of Natural Resources at the University of Missouri. His research focus is on forest landscape modeling and forest ecosystem process modeling. Wen Wang is a research associate in the School of Natural Resources at the University of Missouri. Her research focuses on the roles of disturbance and climate change on the forest carbon dynamics and tree species distribution using process-based ecosystem and landscape models. And Dr. Frank Thompson is a research wildlife biologist with the U.S. Forest Service Northern Research Station at Columbia, Missouri, and a cooperative professor in the School of Natural Resources at the University of Missouri. His research addresses avian ecology and conservation and forest landscape modeling and climate change. I hand it over to our first presenter.
Well, thank you for the introduction. A little bit of background. The most recent and severe climate model predictions has predicted somewhere from 5 to 7.5 degrees of temperature increase, and then also predicted a very varied precipitation. This temperature and precipitation variation varied spatially and seasonally. As we can see that this is our study area, and we can see a large increase in the summer temperature, a large decrease in summer precipitation, and then some moderate increase in fall precipitation. So at the same time, the population growth in our study area is projected to be very rapid and expanding into the surrounding rural and many forested area. And recent studies also have predicted that tree species composition may change greatly in this region landscape, which may affect forest industry and social well-being in the region. Therefore, understanding how these combined forces will affect the distribution and abundance of the primary species is important. Over the last 7 years or so, we have developed a forest landscape model, Landis Pro, in our lab. And this model is designed to simulate all the above combined forces. It is a raster-based model and can divide the landscape into raster cells. In our case, we have about 5,000 by 4,000 cells at 270 meters. And the model actually tracked species level information, density and size at each cell, and simulate forest development and succession at each cell, and then also simulated harvest disturbance and dispersal in subset of cells. And we have used this approach in many eastern U.S. forest regions, from central hardwood to central Appalachian to mid-Atlantic and New England area. So based on those working experience, we move on to our Gulf Coast Plain and Ozark landscape. So the overarching objective is to determine the effects of climate change, urbanization, succession, disturbance, and management on forest change in Gulf Coast Plain Ozark landscape for this century. Specifically, we look at 4 climate scenarios: the current climate and the 3 alternative future climates. We also look at 3 forest management scenarios, which are no management, current management, and a resilience management. And also 2 urban growth scenarios, which is no growth and then predicted growth for the next 100 years. So combined, we have about 24 simulation scenarios. So each one will generate a set of maps that are at 270-meter cell size resolution. So the approach for us to do this project is we downscaled climate model prediction to ecological subsection, and that include temperature, precipitation, and solar radiation and wind speed at a daily time step, at a daily interval. And then that information is used as an input to an ecosystem process model called linkages. And linkages will simulate plots on each ecological subsections and including tree species traits and soil properties. And the outcome of a linkage simulation will be the species establishment performance and the carrying capacity of each subsection. And that species establishment coefficient is going to be used to quantify how well the new and the current environment fit the species. And that information is included into Landis Pro simulation, which simulate growth, aging, seed dispersal, and disturbance such as fire, wind, and management alternatives such as no management and urban growth. So this is an illustration of a eastern Gulf Coast subregion in which this subregion is divided into many ecological subsections. In each of the subsections, we conducted linkage simulation using climate, downscaled to each subsection, and then major soil up to 10 within each subsection, and then to look at species potential establishment and maximum growing space. So the linkage simulation, as this diagram illustrated, the landscape is divided into many raster cells, and then the landscape is also stratified into ecological subsections, as we can see here. And then within each subsection, up to 10 major soils were used and then simulated with the linkages, incorporating climate drivers. And then the simulated species response and the growing capacity is used as an input for Landis. And Landis then simulate harvest, fire, and wind throw and seed dispersal along with the succession. So the linkage actually produce a future possible species suitable habitat, species habitat. It is not the actual where the species is going to occur. And Landis then is going to produce simulated the actual possible species distribution and composition structure. One is called fundamental niches, and the other one is called realized niches. So the response variable we use to look at our analysis are basal area, density, importance value, distribution, and biomass by species. And these variables are tracked by each cells, and they can be summarized to the entire region, to subregion, to subsection, or to any natural or political boundaries. And we also look at species change in distribution and importance value and the future climate scenario at year 2100. And these changes are expressed as extinction, colonization, and persistence. With that, I'll turn this to Jacob Fraser.
Thank you, Hong. And I think it's at this point that we're going to ask question 2.
Well, I don't think we ever launched the first poll.
Oh, okay.
So let's go ahead and launch the first poll, which polls our attendees.
Okay.
This is just to get some information about who's attending the webinar.
All right.
I'm going to give the attendees about a minute to pick a designation for your profession. We have 21 attendees showing right now. I'll give you about 10 more seconds to get your vote in. And I'm closing the poll. And most of our attendees classify themselves as wildlife manager or conservation planner. There's a pretty even distribution among the other 4 categories of commercial forester, consulting forester, state federal forest manager, or research scientist.
Okay.
So
we'll go ahead and do questions 2 and 3 together after this segment, if that's okay.
Okay.
All right. So thank you. Oh, is it okay to go on?
Yeah, go ahead.
All right. So as Hong mentioned, linkages is an ecosystem process model that we use to simulate the effects of climate on individual species and forests as a whole. And that's using the inputs of daily climate as well as site, soil characteristics, and species traits, which essentially models the forest on a standard plot size. It's modeling individual stems by species in a non-spatial way. And so one of the things we get from that is a maximum biomass of the site under each of the different climate scenarios. And what this map is showing is the ratio of maximum biomass under future climate models compared to the current climate conditions. And what you can see is a range of responses across the climate scenarios. The access model, which is the one on the left here, was one of the climate models which had a decrease in growing season precipitation across pretty much the entire region, and overall had the largest declines in maximum forest biomass, especially in the west Gulf Coastal Plains region. In the center, the CAN-ESM model, which had modest increases in precipitation during the growing season, had some areas with increased biomass productivity, and the GFDL model on the right here showed an increased maximum biomass over most of the study area due to higher precipitation levels in the growing season. It's also worth noting that all of the models projected declines in biomass in certain subsections, mainly in the south central and southwest regions of the study area. So in addition to modeling forests as a whole, we simulated 29 individual species within the model. So in general, we saw that some northern hardwood species, such as sugar maple and northern red oak, which had their southern ranges sort of barely within the study area, showed a loss of potential habitat as that southern boundary shifted northward almost completely out of the study area. The responses of the southern pines varied. Shortleaf showed a contraction of its potential range, while slash pine had an expansion. Loblolly and longleaf generally remained unchanged, and in general, most of the hardwoods showed declines in potential habitat. So the next few slides are going to show the changes in potential habitat for certain species under future climate scenarios. And keep in mind these results are modeled without taking into account interspecies competition, disturbance, dispersal, or native ranges. And the classes are defined by dividing the maximum species biomass under future climates by the maximum under the current climate. The first thing we're going to look at is loblolly pine, which, as I mentioned, shows either no change or a slight decrease over most of the region, with the exception being varying degrees of increased potential in the Ozark Highlands. Longleaf pine had a similar pattern, but had a little more negative response under the drier climate model axis here on the left, but still had an increase in potential in the Ozark Highlands. So kind of the opposite, shortleaf pine showed a large loss of potential habitat in all but the Ozark Highlands under each of the climate models. And another widespread species, a hardwood white oak, had a similar response. It was also noting, in general, bottomland and floodplain species fared well under the future climate models. One in particular, Laurel Oak, had an expansion northward of potential habitat. And so, as I said, these are modeled potential habitat in which many factors are not included. And next we will see how some of these factors affected species responses in the forest landscape model, Landis. And before that, we'll go ahead and do questions 2 and 3.
Okay, I'm launching the second poll, which asks the question, will having information on forest landscape changes in response to climate change over the next 100 to 300 years affect how you manage or conserve?
For forests. Couldn't fit that in a question.
It took me three tries to read that. About 3/4 of our attendees have voted. I'll give you about 5 more seconds.
And I guess we'll go ahead and, if we can, wait to do question 3 after this segment, just so we're not doing it all at once.
About 60% say yes, 35% say they're not certain, and 6% say no. So let's go into the third question.
Oh, wait. We'll wait on that if that's okay. Sorry.
Am I hearing you want to go ahead and launch it?
No, we will wait on the third question and do that after this segment.
Okay.
Okay. GCAP just showed you the potential species habitat and growing capacity under the future climate change scenarios. Now I'm going to show you the predicted realized species distribution and the forest composition structure under different scenarios. Landis Pro predicted the simulation results at a 270 meter raster cell. We organized our simulation results by sub-regions. So we have 5 sub-regions in our study area. So I'm going to use the East Gulf Coastal Plain as an example. So this slide shows the predicted basal area and density under four climate scenarios with fire, harvest, and urban growth. So we can see the basal area and density follow the very similar pattern under four climate scenarios. Because succession, including growth, aging, and mortality recruitment, will be the dominant factor driving the future forest dynamics. And the basal area increased rapidly from 2010 to about 2050, and density will decrease from 2010 to about 2050 because of continuing forest growth and competition. But like basal area will tend to stabilize for decades as forests mature and then gradually decrease. So climate change will overall have negative effects because of hotter and drier growing season. And the negative effects also vary among different climate change scenarios. And under the very severe climate change scenario access 1.0, the basal area will be decreased by about 10% by end of this century, which showed in red lines, and compared to the under current climate scenario. And similar basal area and density patterns were found for other four subregions. So from these results, which implicate that under climate change, the forest in this area will maintain carbon sink by mid-21st century because of continuing forest growth, but will turn carbon source by end of the century. Now, let's look at the harvest effects. As expected, harvest will have great effects on forest. This slide shows the predicted basal area and density under access RCP 8.5 with and without harvest in East Gulf Coastal Plains subregion. So at year 2100, harvest could reduce by 30% of basal area and increase 3 times the density compared to with a no harvest scenario through directly removing trees and promoting tree regeneration. Next, let's say the urban growth effect. Recent study show that the urban growth will be the dominant drivers of the land use change because of the population growth and the demands for timber and fiber. So generally, this figure shows the percentage change in forest area by subregion. So generally, urban growth could reduce from 30% to 3% to 10% of forest area. And in East Gulf Coastal Plains subregion, urban growth can reduce by 10% of basal area by year 2100 and have no significant effects on tree density. So now let's look at the climate change effects on species relative importance value. We calculated the ratio changes in species importance value under 3 climate change scenarios with fire, harvest, and urban growth compared to current climate at year 2100. So the ratio changes in species importance value in the left side range from -1 to 1. So the red species will decrease and the green species will increase. So we can say in the East Gulf Coastal Plain subregion. So species will respond to climate change very the species responses to 3 climate change scenarios are pretty similar, with only some minor differences in species ranking. So overall, the yellow poplar, shorty pine, white oak, black gum, and white ash will be the top 5 winners. Oh, losers, sorry. And however, the slash pine, loblolly pine, red maple, or swamp tupelo, or balsympress, they will increase their relative importance and will be the top 5 winners. So now let's look at the species distribution changes and the climate change. So since the responses of a tree species distribution to climate change varied individually, spatially, and temporally, we will pick 3 major pine species and 2 oak species to show their distribution changes in terms of persistence in blue, and colonization in green, and extinction in red, compared to current climate at year 2100. So let's look at the loblolly pine first, which is the most important economic tree species. We can say, let's look at the top 3 maps first, which show the responses of the distribution changes for loblolly pine and the 3 climate change scenarios with fire harvest. So these 3 maps show the pretty similar pattern. So overall, it's good news to loblolly pine. So loblolly pine can generally do well under future climate change. So because we can see lots of blue color. It's very important to notice that. So even linkage results suggest Ozark highlands will be a very suitable habitat for loblolly pine to come and establish. But our linkage results suggest that loblolly pine cannot really move here because of very limited dispersal. So it might take several hundred years to let loblolly pine finally move here. So next, so let's look at the harvest effects on the species distribution changes for loblolly pine. Let's compare the bottom 3 maps without harvest to the top 3 maps with harvest. We can say the harvest would slightly accelerate the colonization of loblolly pine by 3% in the northern area through promoting the generation. We can also see some green color at the same time, harvest will slightly accelerate the extinction of loblolly pine in the west area. Then it's a longleaf. So from the top 3 maps, so loblolly pine will experience some extinction in red color in the west Gulf Coastal Plain region, but generally will persist in the east Gulf Coastal Plain and the Gulf Coast. So we can see some colonization in the west, in the northeast Gulf Coastal region, suggesting some northward migration of loblolly pine. Likewise, through comparing the bottom 3 maps to top 3 maps, harvest will accelerate the extinction of longleaf pine by 15%, particularly in the west region. But harvest will also accelerate the colonization of longleaf pine by 10 to 15% in the north. So next, let's look at the white oak. So the top 3 maps show that white oak will overall persist in the Ozark highland, but will experience a lot of extinction in the south, and can be nearly eliminated in the south in the future climate change scenarios. So although we cannot see much a green color here, because of white oak is a very widely distributed tree species, but we observed a more obvious northward shift in the northeastern United States. So likewise, through comparing the bottom 3 maps to top 3 maps, we can see harvest will accelerate the extinction of white oak by 20%, particularly in the south. So next, let's look at the laurel oak. Overall, laurel oak can persist in this region by end of this century under climate change. So although it will experience some extinction in the west, but it can colonize in the north area. So among about 8 or 9 oak species we simulated, laurel oak may be the most adapted oak species in this region under climate change. Likewise, laurel oak harvest will accelerate the extinction of laurel oak by 10% in the west region, and will accelerate the colonization by 10% in the north. Finally, let's look at the shoreline pine. So from the top 3 maps, overall, shoreline pine will not do well in this region by end of this century under climate change with fire and harvest. So we can see many red colors in the east and west Gulf Coastal Plain regions. And overall, shoreline pine is okay in Ozark Highland. And extinction rates in the south average about 40%. It can be nearly eliminated in the south. And we can see some green color in the north, which indicates shoreline pine can shift northward a little bit. So in this story, likewise, harvest will accelerate the extinction of loblolly pine, shoreline pine by 40%. So with that harvest, we can say that's the bottom 3 maps. With that harvest, shoreline pine can generally persist by end of the century. However, with harvest scenarios, which are the top 3 maps, shoreline pine were not able to establish under climate change. So certainly, this is a wake-up call for us, because shoreline pine is another very important tree species. So we need to manage it to improve the resilience adaptation. So our simulation results suggest that the best resilient management is to stop harvesting, but which is not very realistic, because we need to balance the timber productions with the ecological benefits. So we simulate a resilient management scenario based on shoreline pine restoration plan in Ozark Highlands. So specifically, we harvest other tree species and plant shoreline pine based on the shoreline pine initiative total acreage goals. So this figure shows the average importance value for shoreline pine. The blue color on the left is importance value on year 2000. Okay, then the orange color is importance value with the regular harvest on 2100, and the green color is importance value with the regular harvest and the resilience management at 2100. So we can say the resilient management could greatly improve the importance value for shoreline pine in Ozarks.
Okay, I think at this time, this is Frank Thompson joining the webinar. At this time, we want to go ahead and ask that third poll question.
Okay. Do the changes predicted by our models seem plausible to you given the anticipated changes in climate? With just a few more seconds with about 80% voting. I will close it out and share the results. 93% say yes.
We're pleased with that result. So I'm going to try to summarize some of the main points that have been presented to you during the webinar. Realize that the information you've been shown by Hong, Jacob, and Wen represents highlights of many different types of results that are coming out of this project, and we've only been able to show you a small fraction of what's potentially available. So we'll try to summarize that to give you a better idea about the main points and some of the other possibilities. So we've projected tree species responses to climate change, fire, harvest, and urban growth. Now our simulation results actually model things at a pixel level, and they can be summarized in tables and maps by region, subregion, subsection, sections, or any other natural or political units. Or we can even look at things at the pixel level. And these include species density, basal area, importance values, and even by species age cohorts. So these outputs can be used in many different ways for many different products. We've just highlighted a few of the kinds of ways to summarize them to show you some of the climate and management impacts. So first off, we want to reiterate that linkages is used in our modeling framework to predict potential changes in species growth and survival at the end of the century under those climate change scenarios, and this can also be defined as a fundamental niche. And that's important because it shows the future potential of these species. It also helps us parameterize the landscape change model. But again, realize that is the future potential. It's not the realized or expected change necessarily. So just to summarize some of those potential changes we showed you, many hardwoods had reduced potential growth or ranges under these climate models, and these included species such as sugar maple, red and white oak, and yellow poplar. Even most southern pines had reduced potential growth or ranges as their potential fundamental niches moved north. However, slash and loblolly did do reasonably well and the best of any of those pines, and actually the best of many of the species under those future climates. Now, in some sections under some models, potential total biomass of all species was reduced, and that suggests the possible idea that some forest may shift to more open woodland and some woodland to more open savanna, as those sites can simply support less woody biomass under some of these climate models. Okay, under Landis, Landis again is predicting the actual changes we expect in the landscape based on a multitude of processes that Dr. He explained, and so we characterize this as the species realized niche. So as you saw in some of the results that Wen presented, many species could actually not keep pace with the changes in their fundamental niche, and they could actually not shift northward to occupy some of those newly potential suitable habitats. And we saw in some cases that extinctions exceeded colonizations at the pixel level. So for example, shortleaf pine and white oak, you saw a lot of pixels going extinct in the most southern parts of the region, but only modest gains to the north because species can only disperse so fast. Nevertheless, just over the next 100 years, most of these species still had relatively high persistence rates, even at the end of the century under climate change, particularly with no tree harvest. And that's really simply because trees are long-lived, so they can stay in place for a long time. The change tends to happen when they have to regenerate, because our modeling framework, the way it's set up, we're actually assuming that trees are most susceptible to climate change when they're regenerating in that seedling sapling stage due to potential mortality due to warming and drying. You also saw that harvest accelerated species turnover, and that resulted in higher extinction rates in the southern part of the region for species such as white oak, shortleaf pine, and yellow poplar. However, harvest, and again, its impacts on species turnover, can also create growing space for species that are areas may now newly be suitable for, so it can actually accelerate or facilitate colonization and migration of species northward. And then my last summary slide is that management makes a difference. And we think this is a really important point. We've already talked quite a bit about harvest accelerated change by facilitating species turnover, and that can be both positive or negative depending on your perspective. We thought the resilience management scenario we looked at was particularly interesting because it shows the potential that with targeted management that looks at regions that are still most suitable under future climates and plant species and targets harvest, that we can actually dramatically affect future composition and structure. And so a couple of the ideas that you can consider further as you consider either resilience or adaptation scenarios are that is by planting less adapted species or species less adapted in the future, we can promote their resilience and persistence for a longer period of time by assisting them through that particularly sensitive regeneration phase. However, we can also use planting to plant species that are better adapted in the future to actually facilitate migration. And that's can be a controversial idea around facilitated migration, but I think our results kind of highlight that there is certainly going to be or likely be the opportunity to consider facilitated migration as potential habitats probably will change more quickly than trees can disperse on their own. And then lastly, another aspect of management, rotation intervals, shorter harvest intervals will just further accelerate species turnover. And again, that can be good or bad depending on your perspective. So that's the end of our presentation in summary. We want to thank everybody and those who've been funders and collaborators on this. And I believe you still have one more poll question you want to ask.
We do. We have one more poll question. I'm going to launch it in just a second. And this has to do with the question of how do we disseminate the science. And with about 70% voting, I'll give you about 5 more seconds to select a platform or format for obtaining the results. And I'm going to close the poll and share the results. We have 23% opting for a peer-reviewed journal, 62% web-enabled data or platform, 15% technical report. No response for extension document or social media videos. So the majority of people are selecting a web-enabled data platform.
Thanks to the presenters. We have not yet received any questions in writing, so I would just like to point out to everybody in the audience we have about 14 more minutes. We don't have to use all that time, but if you do have a question, there is a raise your hand button that you could press that, and I could try and unmute you, and you could just interact directly with our presenters. Or you could submit your question in writing.
I guess I did have a question, and I think you answered it towards the end, but it had to do with the shortleaf. When we saw those maps at the beginning that that were basically vector shapes of the biological ecosystem units, where it appeared that shortleaf was pretty much being extirpated from most of the coastal plain, or all of it. And then when we got into the raster maps, shortleaf was showing a lot of blue, meaning persistence. And I was a little confused, but I believe that what you were indicating towards the end there was that shortleaf is a species of conservation concern, and it can be maintained in the landscape with management. Am I getting that right?
I'll take the first stab at that. That's pretty much right. So recall that the linkages model is modeling potential habitat. So that result where you saw those large areas of extirpation is linkages saying that those sites at the end of the century, basically shortleaf pine will not be able to grow or survive through the seedling sapling stage. However, where it already exists, larger established trees may very likely persist much longer. But linkages is in fact predicting it's going to be very difficult to regenerate in those areas in the future, at least naturally. So that's, and then the Landis results do not look as drastic because Landis is predicting realized change. And over 100 years, shortleaf will still persist on many of those sites. Even if in 100 years it can't regenerate there. But the very long-term picture for it is probably not very good. And in fact, if you run Landis out another couple hundred years, you will see the Landis projections start to look more like the linkages projections. So if we see that amount of warming, the long-term picture for shortleaf in the coastal plain is not good.
You don't have any raised hands, so I'm going to ask my question. Wen Wang made a statement just real briefly where she was showing the basal area, and she basically said that a lot of the forests would remain sinks for carbon up to about the middle of the century, and then if I understood her, then she said they would turn into sources. And my question is that based on some kind of measurements or parameters that you had in your models, or is it just an assumption that there's going to be increased senescence and decomposition that's going to result in those forests becoming source of carbon?
So I just showed you the basal area and density patterns. So in our Landis model results, the basal area is very similar to the above ground biomass and above ground carbon. So then, based on that, I make a conclusion that this region, the forest, can keep serving as carbon sink by mid-century, but will turn into carbon source by end of this century. But we in our model we did not include CO2 or nitrogen decomposition. We only include the climate change, succession, and disturbance effects on the carbon. In that perspective.
Well, if I can add to it, I think the peak of a biomass or basal area in this case is due to forest growth. And then when forest grows to plateau, that's driven by their longevity. And then most of the tree at that point reach longevity because the forests are pretty even age. And then at that point, mortality rate is outpaced the growth and regeneration will cause a slight decrease of a basal area or biomass that may turn the entire region at the regional scale into a carbon source.
Thank you. Thank you to all of you. Very interesting presentation. Is there anything else you guys would like to add?
No, we're happy to share those results with you.
I think that's great, and I think we can talk more offline about how to share news of your study and share in more detail the information that you have, and especially given that we have a platform, a web-based platform to share data, so that'll be a conversation for the future.
Yeah, and I guess we can end with one more plug for future work. So we'll be continuing the work with the LCC with these different results from management and climate change and linking them to different wildlife species models as well as other kinds of adaptation and resilience management. So to say it's a really rich data source, and we hope it's just the beginning of its use to help conservation planning.
Great. Thank you very much.
Okay, thank you.
Bye-bye.
Goodbye.
Bye-bye.